Hello students, welcome to the mathematics class. Today our topic will be circles. Let's understand what circles are. If we take any fixed point on a plane and draw infinite points around it like this, we take infinite points around it so that each point is at a fixed distance from that point. The figure so obtained is called a circle. You can see this is the collection of infinite points around a fixed point, and the figure obtained is called a circle. This fixed point is called center of the circle. Any round figure is an example of a circular object. A circle is an idea, and the round figures, we can say that this disc is circular in shape. Any object which is round in shape and can be drawn on a plain paper or board is called a circle. The fixed point around the circle, that is at the middle of it, is called the center of the circle and is usually denoted by O. So, to know more about the circle, let us draw a circle with a fixed point in the center, that is called the center of the circle. If you draw a line on the circle so that one point is the center and another lies on the circle, this is called the radius of the circle. The length along the circle, that is round in shape, is called the circumference of the circle. The circumference of the circle is the perimeter of the circle also. We can call it either perimeter of the circle or circumference of the circle. When you draw a circle on a plane surface, it divides the plane into three regions. One is the interior of the circle, we call it the interior. Another is the exterior part of the circle. The part that is outside the circular boundaries is the exterior of the circle. And the third one is the circle itself. So we can say that a circle divides the plane into three regions: the interior, the exterior, and the circle itself. The fixed point on the circle is called the center of the circle, where from every point on the circle is at equal distance. If you draw a line whose one end point is the center of the circle and the other point lies on the circumference of the circle, is called the radius of the circle. Here radius of the circle is denoted by OP. Is denoted by OP, and usually we denote it by letter R. So this is the radius of the circle. The circumference of the circle is measured in terms of radius, and the area of the circle is also measured with the help of the radius. Now, if you want to find the circumference of circle, you can calculate it by using relation 2 pi r. And if you want to find the area of circle, you can denote it by, or you can find it by the relation pi r square. Now, if we take a part of the circumference, suppose we take this part of the circumference, this is called the arc of the circle. Denoting it by r and s, the part of the circumference is called the arc of the circle. Now, there can be two different arcs, one rs, that is the smaller arc, and another rs, that can be the bigger arc. The smaller arc is called minor arc. We can say minor arc rs, or simply you can write it as rs with denotation arc on it. and there is another one. Suppose we take Q on that, and this arc RQS is called the major arc of the circle. This is major arc RQS, or you can write it as RQS with the symbol arc on that. So the circumference can be divided into two parts. The smaller part is called minor arc, and the major part is called the major arc. Now, if we draw a line across the circle so that its both endpoints lie on the circle, suppose A and B are the endpoints of line segment AB. This line segment AB is called chord of the circle. So here we denote chord of the circle by AB. So chord of the circle here is AB. It is any line segment whose both endpoints lie on the circle. If we draw on the chords, it becomes larger and larger. Ultimately, we move through the center of the circle. This will be the largest chord of the circle. In fact, here the largest chord of the circle that passes through the center is called diameter. The diameter is the largest chord of the circle. Note down, diameter is the longest chord of circle. And this diameter can be denoted by D, and we can find out that diameter is always twice its radius. The diameter divides the circumference in two equal arcs. One is this one arc TQP, and another is this arc TAP. Both arcs are equal in length, so we call this a semicircle. A diameter divides the circumference into two equal parts, and each equal part of the circumference is called semicircle of the circle. So another part is semicircle. Note down what semicircle means. It is the part of the circumference that is divided by the diameter into two equal arcs. Then moving to another part. This is the circle. If we take a chord AB, circle with center and chord AB, and you find that we have two parts of that circle. One is the chord, another is the arc. This is the minor arc, and this is the chord. The area in between the chord and the arc is called segment. So this area is called segment. You can see this part of the segment is smaller in area, and the rest of the circle is larger in area. So we can denote this smaller part by minor segment, and the rest, chord and the corresponding arc, the major arc, becomes the major segment. So another thing we need to know is what is segment. A segment is an area between the chord and its corresponding arc. We have two segments, one having smaller area as minor segment and another having major area known as major segment. So segments are minor segment and major segment. And the definition of segment is area between arc and its corresponding chord, or arc and is called. Chord. So this is segment. Now we come to another part of the circle that is called sector. Now what is sector? If we draw a circle and from the center we draw any two radius. The plural of the radius is radii. Now when you draw any two radii, the area between these two radii and the corresponding arc is called sector. So what is sector? It's area lying between two consecutive radii. We call it sector. Again, we have two different types of sectors. One takes the smaller area, that is called minor sector, and another carries the larger area, we call it major sector. So sector is the area that is lying between any two consecutive radii. This way we came to know about the sector. The angle at the center made by these sectors is called sector angle. Angle made by sectors at center is called its sector angle. Sector angle. So the angle carried by minor sector is acute angle, and the angle carried at center by major sector is a reflex angle. These are some of the points that we should know about the sector. Now let us recap quickly what we learned about circles. We learned about what circle is. It is the arrangement, the collection of infinite points around a fixed point, and the circle has a center. Then we learned that the circle has a radius. There is a line segment whose one end point is the center and the other point lies on the circumference. Number 4, we learned about circumference. The part of the circumference is called arc. We learned about arc. We have minor arc and major arc. The smaller part of the circumference is minor arc, and the larger part of the arc is major arc. Then we learned about chord. Chord is a line segment which has both endpoints lying on the circumference. In fact, the largest chord is the diameter, and diameter is twice its radius. Then we learned about segment. Segment is the area between the chord and the corresponding arc. We have two types of segments. One is the minor segment and another is the major segment. Number 8, we learnt about sector. Now the area lying between two consecutive radii is called sector. We have two types of sectors. One is minor sector and another is major sector. And apart from that, we learned that diameter is the longest chord of the circle that passes through the center of the circle. It is twice its radius. So these are some of the important points you should know about the circle. Now let us take some relations between chord and the angle subtended by it. Suppose we draw a circle and a center in it, and and suppose we draw a chord AB. Now, if we join this chord AB with center O by joining OA and OB, this angle at the center made by this chord AB is AOB, and we call it angle subtended by chord at the center. You can understand, you can see the length of the chord AB and the angle made by it at the center. Now, let's draw another chord PQ. You can see PQ is little bit larger in size than line segment AB. PQ is larger in length. Now again, if we draw an angle for PQ at the center, this is the angle subtended by the chord at the center, and you can find out as the length of the chord increases, the angle at the center also increases. If you take another chord, suppose RS, and draw an angle for the chord at the center, so you can see the angle subtended by that chord at the center becomes more larger. Now, if you decrease the length of the chord, the angle at the center will automatically get decreased. So, you can say the length of the chord and the angle subtended by it at the center are directly proportional to each other. Now, we have an important theorem for that equal chords of a circle subtend equal angles at the center. We will prove that theorem. This is an important theorem of the circle. Equal chords of a circle subtend equal angles at center. Suppose we draw a circle with center O. You can denote this circle by C, and in brackets you can write O and R. This means circle C with center O and with any radius R. And there is two equal chords. Let's draw two equal chords, AB and CD. Suppose these are two equal chords drawn on the same circle. AB subtends angle AOB at center, and CD subtends angle COD at center. We need to prove that angle AOB is equal to angle COD. That means equal chords of the circle subtend equal angles at the center. To prove that, we are given a circle C with center O, radius R, and we are given two equal chords AB and CD, and we need to prove that these two equal chords subtend equal angles at the center. That is, angle AOB is equal to angle COD. For that, we take two triangles made by them. That is the proof. Take triangle AOB and triangle COD. Now, we will compare them. Why is OA equal to OC? Because both are the same radii of the circle. A circle, we can draw infinite number of radii on the circle, and all the radii are of same length. So, when you write OA equal to OC, the reason is that they are the radii of same circle. Radii is the plural of radius. Radii of same circle. Then we have OB is equal to OD. Same reason. Radii of the same circle. And AB is equal to CD. Why is AB equal to CD? Because we are given equal chords of circle. They are equal. So, corresponding to that, we write given. Given in the question. So, the triangles get congruent. You can see that we have shown all the three corresponding sides of triangle equal to each other. So this rule indicates that the triangles are congruent by Sss Congruence Rule. When they are congruent, you can write angle AOB is equal to angle COD. Because when triangles are congruent, their any corresponding side or angle is equal. And AOB is equal to COD, we can write CPCT, corresponding parts of congruent triangles. So this way, we proved that in a circle, if we draw two equal chords, they subtend equal angles at the center. Hope you understand that. Now, the converse for that theorem is also true. It means that if you draw a circle, like we draw a circle with center O and radius R, and if we draw two chords and they subtend equal angles at the center. We draw two chords AB and CD, and both these chords subtend equal angles at the center. You can see chord AB subtends angle AOB at center, and chord CD subtends angle COD at center. If these subtended angles are equal, what can we say about their chords? Now, equal chords subtend equal angles at the center. Then we can also say that chords which subtend equal angles at center are also equal. That we need to prove. So, we are given with that the chords AB and CD subtend equal angles at center, and we need to prove then these two chords are equal. For that, again we take these two triangles, triangle AOB and triangle COD, and triangle COD, and we need to look into these two triangles, which criteria will bring them to the congruency. Again, we see that OA and OC are the radii of the same circle and they can be equal. So, writing OA is equal to OC is the reason is radii of same circle. Then we have angle AOB is equal to angle COD. This is given that the chords subtend equal angles at the center. And we have OB is equal to OD, because these are the radii of same circle, and hence the triangles get congruent. Which rule? It is side angle side rule. So, side angle side rule is a strict rule that it definitely needs angle which you are going to prove or which is equal should be between the two given sides. It should be the including angle of the two given sides. So, these two triangles are congruent. Triangle AOB is congruent to triangle COD, and this is Sss Congruence Rule. And when these are congruent, then their any corresponding side or angle is equal, and for that reason we write CPCT, corresponding sides of congruent triangle. So, In this case, we again proved that if the angles subtended by the chord at the center are equal, then these chords are also equal. Sometimes we get a term like congruent circles. Congruent circle is nothing but these are two or more than two circles having same radii, same equal radius, and we can denote it by R. You can, if you have two circles and we are given that both circles are congruent, so you can write it as this is circle with center O and radius R, denoted by C1, and this can be denoted by O dash. This is circle C2 with center O dash, different center from that, but the radius remains same in both cases. In both circles, the length of the radius is same. We can call these circles congruent circles. And to get relevant answers from these two circles, we can proceed it as like this, what we did in last two theorems. Hope you understand this. Now we will know more about the circles with a particular theorem. It says if we draw a perpendicular from the center of the circle to the given chord, it bisects the chord. This can be explained as, suppose we draw a circle with center O and also we draw a chord AB. This is the circle with center O and chord AB. What we need to do is that we have to draw a perpendicular on that chord. Suppose OD is perpendicular on that chord. We need to prove that this chord gets bisected. Bisected means that it gets divided into two equal parts. So, to prove that, we need to join OA and OB and proceed in the same way to find the two triangles are congruent. We are given a circle with center O, can be denoted by C with center O and radius R, and AB is its chord. And we are given that a perpendicular line is drawn from center of the circle to the chord. Now, what we need to prove is that this perpendicular line, where it intersects chord AB, divides chord AB into two equal parts. That means chord AB gets bisected. So, it is theorem 10.3 in your textbook which says the perpendicular from the center of a circle to a chord bisects the chord. So, this is given. We need to prove that AD is equal to BD. To prove that, we need to join OA and OB. Now take two triangles, triangle ODA and triangle ODB, and find out which of the rule makes these triangles congruent. Now first is that in both the triangles, angle ODA and angle ODB form 90-degree angles. So they are equal. We can write ODA is equal to ODB, each 90. Then we have OA, the radius of the circle, and OB, also the radius of the circle. They both are equal, and the reason for that, we write radii of same circle. Then in both the cases, OD happens to be the common side for both the triangles. OD is the side of triangle ODA and OD is the same side for triangle ODB. So we can write OD is equal to OD common side, or simply we can write common. So the triangles get congruent. Which rule makes them congruent? We have 4 congruency rules, and the most appropriate rule for making these triangles congruent is RHS. It is a right angle, and the side opposite to the right angle is the hypotenuse, and the remaining one side. Out of these 2 sides, one side should be equal. Either AD should be equal or OD should be equal. So we can say these triangles are congruent by RHS congruency rule. By RHS, we mean right angle, the hypotenuse, and the side of the 2 triangles are equal, then the triangles are congruent by RHS rule. And when they are congruent, then any corresponding side or the corresponding angle of these 2 triangles are equal. When concerned with corresponding sides AD and BD, they are equal by CPCT, and this way we proved that if a perpendicular is drawn from the center of the circle to the chord, it bisects the chord. Hence we proved that. We can also prove the converse of that theorem also, which says that if we take any chord AB and take D as midpoint of the chord, which is joined with the center, the line segment so formed is perpendicular to the chord. I repeat, there is the circle with center O and chord AB. D happens to be the midpoint of AB, and if a line segment is joined from the center of the circle to that midpoint, we have to prove that this line segment is perpendicular to the chord. For this, we can write, we are given chord AB, or we can write straight away D is midpoint of AB. And O is joined to that, and we need to prove that OD is perpendicular to AB. Now, in proving that statement, we join OA and OB, and thus 2 triangles are formed. One is triangle OAD, so when OA and OB is joined, 2 triangles are formed. One is triangle OAD and another is triangle OBD. Now, to make them congruent, we find that OA is equal to OB. Again, both are the radii of same circle. The reason is the same. You can write radii of the same circle in brackets adjacent to it. And then we have AD is equal to BD. It is given that the line segment OD it is given that D is midpoint of AB. Then OD is equal to OD. Common side for both the triangles. So the triangles get congruent. We can say triangle OAD is congruent to triangle OBD, which is Sss Congruence Rule. Now, when they are congruent, then their corresponding angles are equal. Like ODA is equal to angle ODB, CP, CT. So this angle ODA is equal to angle ODB. This is ODA and this is ODB. Now you can find out both these angles lie on the straight line AB. And when any two adjacent angles lie on the same line, their sum is always equal to 180 degree. We call them linear pair of angles. So, angle ODB and angle ODA, their sum is equal to 180 degree, and the reason is that these form linear pair of angles. Linear pair of angles are always drawn on a straight line, and both angles happen to be adjacent angles. Now, you can keep ODA, because we have proved ODA is equal to ODB. So, instead of ODA, write ODB, keep angle ODB as it is, and the sum of both is 180. This is twice angle ODB is 180, and each angle ODB will be equal to 180 by 2, that is 90 degree. So, when OD and AB gets intersected, they get intersected at right angles, and hence we are able to prove that OD is perpendicular to AB. So, this is the proof for the theorem that carries the statement that the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Hope that you understand that theorem. Thank you. Now, there is another important thing about circles, that how many circles can we draw through 1 point, through 2 points, through 3 points, and through infinite points. Because itself the circle is the collection of infinite points. Let us concentrate on how many circles can be drawn through 1, 2, and 3 points. Suppose we are given point A or O. Now, through that point O, how many circles can be drawn? You can find out that we can draw infinite number of circles through that point with less, smaller and greater radii. So, you can see through that point infinite circles can be drawn. So, first result is that infinite circles can pass through 1 point. If you draw a point and draw as many circles as you can that pass through that point, you can find out infinite circles can be drawn. If you take any 2 points now, suppose we take point A and B, and we want to find out how many circles can pass through these 2 given points. This is point A and this is point B, and draw a circle like this, like this, like this, increasing the radii, and you can say you can draw infinite number of circles passing through these 2 points. Now, let us draw 3 points now, and all the 3 points should be non-collinear. There is another important result for the 3 non-collinear points. If we draw 3 non-collinear points A, B, and C, and we need to know that how many circles can pass through 3 non-collinear points. For that, let us join all these points, join A to B, then B to C, and with the help of the compass, draw the perpendicular bisector of BC. Taking B as center and radius more than half of BC, draw an arc from up and from below the BC. With the same radius, now take C as the center and draw another arc. Both these arcs, suppose, intersect at point P and Q, and join this point P and Q. PQ will be the perpendicular bisector of line segment BC. And repeat the same for line segment AB. Taking A as center and radius more than half of AB, draw arcs like this from B as center. This is the arc and another arc. From A, let's take this arc and this arc, and both arcs meet at suppose points R and S. Now if you join R and S, this is the perpendicular bisector for line segment AB. So where both these perpendicular bisectors meet, take this as a point O, and now take O as center of the circle and OA, OB or OC, any one of them as radius of the circle, O as the center, OB or OA or OC as the radii, and draw the circle. You can find out that only one circle passes through three non-collinear points. This way, we understood that only one circle can pass through three non-collinear points. It's an important result of the circles. Hope you understand this. Whenever you are given a circle without center and you are told to find the center, again you can put three non-collinear points on the circumference, join them, draw their perpendicular bisectors. The perpendicular bisectors where they meet is the center of the circle. Hope that you understand today's